Hello, Dr. Snidely speaking. With our fully generalized vectors, I think we are totally ready to put them to good use in our sphere tracing algorithm, which is supposed to be developed right now. Of course, we will not develop our own, even though my famous intellect could possibly certainly do so. Instead, we will look at the existing Ceepepporg implementation to see what they're actually doing to make that happen. From what I see here, all we need is a ray and a hit, and they also have the scene object that allows stuff to be intersected, but to be honest, in Rustacean, it's probably best to just make that a trait, so that we can implement this trait for whatever we want. I mean, look at what they do. They derive a sphere from a scene, which means that a sphere is a scene, which, to my mind, makes no sense. But that's what happens with taxonomies sometimes. You can't have it all if you have a static hierarchy with just one parent at a time and all these problems that you have. So using traits is the best thing for us to do here. For Rustaceans, writing tests is part of the workflow because that really helps to realize possible errors in the API, and it helps you to basically fix them before you hit a client with it or before the production facility has an issue with it. So in this case, it looks like it would be useful to have a default vector, like a vector which is just initialized with 3 rows. So how do we get that? That was, of course, a rhetorical question, because what we need to implement to get a default of anything is the default trait. Yes, there's a trait for basically everything you ever wanted. Who would have thought of that? However, it shall also be mentioned that whenever generics are involved, things sometimes are not as easy anymore as you would think or hope they are. Of course, that's not a problem for a seasoned Rustacean as I am, yet as you can see, a little bit of try and error, never hurt anybody. So what's the right syntax to use the default then? Yes. I tried a lot there to finally realize what has to be done, and I realized that traits really have to be used by themselves. So vector default doesn't do anything. In the end of the day, you have to use the trait itself and basically tell the trait which type you want to have at the end. I know, it's difficult to understand. Let me scrub forward a bit just to show where this ends up being. Now, in order to implement the intersect trait for a sphere, the Ceepepporg show that apparently it makes it easier if you have a RaySphere method that I just renamed to intersect ray, and I shall further rename it to something more appropriate later. However, all we have to do now is to fill in the math. Of course, I could do that with my eyes closed, yet I decide to basically take the Ceepepporg math right off the bat, just because reasons. It is also worth noting that we changed the result type of the intersect call in the intersectable trait to something more Rustacean. So instead of returning a hit and then, let the call decide what kind of hit it is by checking the distance of the hit from your source ray, instead we will return an optional that will either be none or contain the valid hit. Now, the only thing left for us to do is to verify our math here is actually working. And what could help more than a simple little unit test that does the obvious? So we create a sphere with a radius of 1 at position 0 in space. And then we create a ray, which shall be positioned in front of the sphere and looking towards the sphere on the x-axis, and another ray which looks away from the sphere on the x-axis. So in theory, ray 1 should hit the sphere at exactly a known position, which is at x1, and ray 2 should miss the sphere, and this is all we have to test here. It is also worth noting to have a look at the type hints we provide to tell the compiler what type we wish. So in the first case, the sphere, we say that S is supposed to be a sphere using floating point numbers, which are 32-bit in our case. Whereas on the other hand, for the first ray, We just say that we want a vector that uses 2.0 as floating point numbers, which kind of implies all the other types used for the ray. Using and specializing a generic in a non-generic function is rather easy and straightforward and intuitive altogether, so that's something I do really like to do. When trying to create a function that sets up a scene for me, which is itself generic, things became a little more difficult. It took me so much longer to get this generic setup scene function working, just because, because I wanted to show you what not to do before I did it right. So lessons learned here clearly are, first, if you want to use traits, then you usually have to use the special bracket syntax that basically tells what kind of trait you want. So if you use float 0, for instance, or float 1, you have to say that you wish to cast t to a float trait, basically, to use the function on that casts a trait. It looks a bit special, it looks a bit odd, and it's something you don't really find in any literature right now. That's how new it is or how fancy it is. But actually it works, and I didn't find another way to make it work. So type inference on traits isn't always what you would expect, but maybe that's purely intended and my puny mind just isn't able to understand why that would be the only logical and right thing. The second lesson learned clearly is that in generics, in fully generic functions, traits are the only thing that you are really going to use if you are making calls on something of your type or of your types. And of course, you must specify that your type T has to support particular traits, whichever trait it is. Interestingly, I had the feeling that the default trait is part of my floats, and T is of type float usually, but you have to specify it explicitly in order to be able to use the default trait on your float types, basically. That was very interesting, but, better explicit than implicit, right? Even though I thought that maybe these things are inherited, but probably not. Oh yeah. Even if I sound confused now, obviously I am not, because I am Dr. Snidely, just to tell you, With setup scene in place, we should now be able to properly test our high-level intersect method on the sphere itself. We will do it in a very idiomatic Rustacean way using a match expression. So as you can see, the result of the intersect call is destructured into its individual components for us to use within the actual case that we hit something. So in this particular test case, none is unreachable, which will cause panic right away, just because we know that R1 will always hit the sphere. If it doesn't, something is very wrong. The next case just verifies that we don't necessarily have to hit something if the max distance is too low, and the other one is that Ray2 should also always miss. The option return value is quite nice because it allows us to just check for none or check for some, as we do here, which greatly shortens the amount of code we have to write to make our assertions. Fortunately, writing benchmarks is exactly as easy as writing a test, which allows us to do some performance testing right away. It's important to us because we want to shoot as many rays at these spheres as possible in order to maximize our final RaySphere output. It is very interesting to see how much slower our primary intersection method is compared to finding the distance between a ray and a sphere itself. I mean, it's incredible. It's multiple times slower right away, and all we do is a bit more math in the intersection routine and returning a more complex return value. There might be room for optimization, but of course we will do that only at the very end once we have a RaySphere production facility up and running. I must say that is a very interesting development overall, and I can't wait to see how our intersection performance will behave when we deal with assemblies of spheres and sub-assemblies and sub-sub-assemblies of spheres that are grouped together in complex pyramid arrangements that will have to wait to our next phase of RaySphere productions.
That and more in our next episode of Trace Quest 5.